Okay, let's go. Maybe you want to make it full screen as well. Do you want to present it like that?
Yes. Is it showing up as full screen?
Yes, it is. Perfect.
Okay, great. Thank you.
Thanks. Okay, I guess we're all set up. So, but we still have 2 minutes, so maybe we can just have a 2-minute break. So, up next we have Sam Brandsen from Duke University, who is going to talk about inevitability of knowing less than nothing. So please go ahead.
Thank you for the introduction. Yeah, so my presentation is going to be on the inevitability of knowing less than nothing, which is a reference to negative quantum conditional entropy. And I want to acknowledge my co-authors for this work, Gilad Gore, Isabel Gung, and Mark Wilde. And in particular, I want to thank Mark Wilde for sharing some of his slides for this presentation. So the main goal of this talk, just to give an overview, is we first want to give an axiomatic formulation of quantum conditional entropy. Obviously, there have been multiple previous works that have investigated quantum conditional entropy, but most of them have focused on starting with a specific formula and then deriving properties of that formula. We wanted to show instead what we could find about the most general set of quantum conditional entropy functions based on an axiomatic approach. And we're going to show that every function satisfying the two axioms we propose must take on negative values for EPR states, which means that any plausible conditional entropy based on this axiomatic approach takes on negative values in quantum information. And this negativity of quantum conditional entropy is what we'll be referring to as knowing less than nothing. So to begin with, we'll start with what entropy is in the classical case, and then we'll move to classical conditional entropy, and then finally into the quantum case, and we'll end with our result of knowing less than nothing. So entropy in general is going to be the knowledge gained upon learning the outcome of a random experiment. So if you consider kind of just the simple example of rolling a dice, if you already know the dice outcome beforehand, if the dice is fixed, so just suppose if you know that every time the dice is rolled, you'll get a 3. You don't actually learn anything by performing the toss. You already know it beforehand because it's deterministic. And so the entropy is 0. But on the other hand, if you're rolling a dice that is uniformly random, so that all sides are equally likely, if the dice has d sides, then you'll learn log 2 d bits. So that's the maximally uncertain state and the roll that you learn the most from. And we can also imagine that if the successive tosses are independent, you would expect the entropy to also be additive. So the uncertainty of observing 2 different completely independent tosses is going to just be the uncertainty of individually observing the first toss plus the uncertainty of individually observing the second toss. And throughout this presentation, we're going to be considering only random variables that are finite. So we won't be addressing the infinite case at all. Now we can begin with 2 basic axioms for entropy. So an entropy function h is a function that's not equal to the 0 function, because otherwise we could have a trivial function. It's an uncertainty measure, which we'll define more in the next slide. And it's also additive for product distributions. So this is the product distribution corresponds to the case of 2 independent variables. So this is just the additivity of independent results. And the reference for this is a work by Gore and Tom Miefel. So what an uncertainty is. So we noted that the entropy function is non-decreasing under mixing operations, where a mixing operation is going to be a random relabeling of values. And you would expect that if you're performing random processes or random relabelings, the entropy or uncertainty, the uncertainty cannot decrease. So mathematically, a mixing operation means that with some probability qi, you'll perform a permutation pi. And the mixing operations are going to preserve the uniform distribution. So if you have the uniform distribution and you permute it, you're going to get the uniform distribution back. And intuitively, one way to understand this is that the uniform distribution is the most uncertain state. So you would expect that an operation which cannot decrease entropy must also must map the maximally uncertain state to itself. And so mixing operations must then preserve the uniform distribution and map it to itself as its entropy non-decreasing. So we can then define the function f to be an uncertainty measure for a probability distribution p if it does not decrease under the action of a mixing operation, and if it's invariant under embeddings. And what the second property means is simply that if you add an extra fixed result, if you kind of embed your observation in a larger space where the remainder of the space is constant, that your uncertainty doesn't change. So if we go back to the rather simple example of rolling a dice, if you now suppose that you're not only observing the outcome of the dice, but you're also observing whether the table that you roll the dice on is right side up or upside down. Well, assuming normal situations where the table is always going to be right side up, your uncertainty will be unchanged there. It will just reduce to the uncertainty of the dice roll, because that's where the actual observation, non-trivial observation is. So what are the consequences of these axioms? The first consequence is that H is non-negative for all probability distributions and is equal to 0 for degenerate distributions or deterministic distributions. And H is going to be maximal for the uniform distribution of size D. Among all distributions of size D, the uniform distribution is going to be the maximally uncertain one. And as kind of a standard convention, if we normalize H so that the uncertainty of the maximally uncertain binary distribution is 1, then the entropy of the maximally uncertain d-dimensional distribution is going to be log 2 of D. We can now move into what conditional entropy is. So conditional entropy is going to refer to, it's related to the knowledge that we gain of outcome X, given that the value of Y has already been observed. So if X and Y are two random variables, the conditional entropy of X given Y is how uncertain X is, given that you have knowledge of Y. And if X and Y are independent, you can imagine that knowing Y doesn't tell you anything about X because they're independent. And so in this case, there will be no difference between entropy and conditional entropy. But in general, if X and Y are not independent, your knowledge of Y might inform your knowledge of X. And so your knowledge of Y might decrease your uncertainty of X. And so conditional entropy of X given Y cannot be greater than the entropy of X. And like the previous case, we would expect this to also be additive for independent trials. So if X1 and Y1 are independent of X2 and Y2, the conditional entropy will simply be the sum of the independent conditional entropies. And this leads to two basic axioms for conditional entropy in the classical case. So our conditional entropy function H is again going to be a function that's non-zero and or not equal to the zero function, and is a conditional uncertainty measure, which we can define analogously to the previous case in terms of conditional mixing operations. And it's also going to be additive for product distributions. So additive for independent cases. So we can now define a mixing operation. We know that previously the mixing operation preserved the uniform distribution. So it would map the maximally uncertain state to the maximally uncertain state. Now in this case where we're working with bivariate distributions, one sort of naive guess for what the bivariate distribution of maximal conditional uncertainty is would be simply the uniform distribution on X and Y. So which can also be written as a tensor product of the uniform distribution on X with the uniform distribution on Y. However, we know that this might actually not be the most general way to write a maximal conditionally uncertain distribution. We know that after all, conditional uncertainty refers to your uncertainty of X, given your knowledge of Y. So as long as X is maximally uncertain, it's the uniform distribution. And as long as Y is independent of X and not giving you any additional information, you should have maximal conditional uncertainty. And so we can show that actually there could be many other distributions that also achieve maximal conditional uncertainty. So really, as long as Y is an arbitrary distribution that's independent of X, and X is a uniform distribution, we have maximal conditional uncertainty. And so that leads us to justify having this set here as our set of maximal conditional uncertainty distributions. And then we can define our conditional mixing operations to be operations which preserve this set. So a channel M is going to be a conditional mixing operation if for any distribution U tensor Q, which has maximal uncertainty, you're mapped to another distribution that also has maximal uncertainty of U tensor R, so where there's some distribution R satisfying this. So again, conditional mixing operations preserve the set of bivariate distributions of maximal conditional uncertainty. And the function f is going to be then a conditional uncertainty measure for a bivariate probability distribution if it doesn't decrease under the action of a conditional mixing operation, and if it's invariant under local embedding of x, similarly to the previous case. And so the consequences of these axioms are that h is non-negative for all bivariate probability distributions. So any function h will also reduce to an entropy for product distributions. So if x and y are independent, the conditional entropy is going to just reduce to the entropy of x. So h of p here. And h will be maximal for uniform distributions of size d, or for the maximally conditional uncertainty distributions of size d. And again, if we normalize this, then we find that the entropy of the maximally uncertain conditional distributions is going to again be log 2d. So having gone through the classical case, we can now move towards the quantum case and discuss what quantum entropy is. So inspired by the classical case, we want to use an axiomatic approach here. And we're going to have two axioms that are directly analogous to the classical case. The first one is that h is an uncertainty measure. And the second one is additivity. So in this case, if you have a tensor product quantum state, your entropy of that tensor product quantum state should be the entropy of the sum of the entropies of the individual states. So what is a quantum mixing operation? What is our quantum uncertainty measure? Just as in the classical case, we defined a mixing operation to be one that preserved the uniform state. We can say that channel M is a quantum mixing operation if it's a quantum channel that preserves the uniform state. And our uncertainty measure then will be that a function f is an uncertainty measure for quantum state rho if it doesn't decrease under the action of a quantum mixing operation, and if it's invariant under embeddings. So h is going to be non-negative for all quantum states, and we can also show that h will be equal to 0 for pure states. H will also be maximal for the uniform state of dimension d, again among under all quantum states with dimension d. And if we normalize h, we again find that the maximal entropy is log 2d. We finally introduce the basic axioms for conditional entropy. So a conditional entropy function, h is going to be a function that's not equal to the 0 function, and that will be a conditional uncertainty measure, and that will be additive for product states. So again, additivity for independent states. We can now define our quantum conditional mixing operations. So we know that in the classical case, our conditional mixing operations would preserve the set of maximally uncertain bivariate distributions, which were of the form U tensor Q for an arbitrary distribution, classical distribution Q. So in the quantum case, we are going to say that a channel M is a conditional mixing operation if for any state sigma b, there exists a state omega such that the channel M acting on U tensor sigma will give you U tensor omega. So we're preserving the set of maximally conditionally uncertain quantum states of the form U tensor sigma, where now sigma is just an arbitrary quantum state. So conditional mixing operations will preserve the set of states of maximal conditional uncertainty. And we can define the function f to be a conditional uncertainty measure for a bipartite state rho if it doesn't decrease under the action of a conditional mixing operation. So it doesn't decrease under the action of quantum channel M if M is a mixing operation, and that it's invariant under local embedding of A. And in the quantum case, we can represent this local embedding as performing an isometry channel. So UA corresponds to an isometry. And the consequences of these axioms is, first of all, that H is going to be non-negative for all separable unentangled states. But our key result is that H can be negative for some entangled states. And this has operational applications to, for example, the quantum merging protocol. And we'll show in the next couple slides that H is negative for the EPR state. So what's sometimes called the maximally entangled state. We can also show that, again, H reduces to just the standard quantum entropy for product states. So reduces to H rho A. And H is going to be maximal for the set of maximally uncertain quantum states. So, and specifically the set is the set of quantum states of the form UA tensor sigma, where sigma is an arbitrary quantum state in system B. So in order to prove that we always obtain negative conditional entropy for any quantum conditional entropy function that just satisfies these two intuitive axioms, I'll first define a channel that we're going to use in the simple proof on the next slide. So we can consider a channel, a quantum channel that goes from A tilde, A and B to A prime, where we suppose that this channel first discards system A tilde. And then we can suppose that the channel next performs a quantum measurement where the first outcome of the quantum measurement corresponds to the EPR state. And the second one is going to just then, of course, be the identity minus the EPR state. If we observe the first outcome corresponding to the EPR state, we'll prepare a pure state afterwards. And if we observe the second outcome, we'll prepare the orthogonal state. And we can show that this is going to be a conditional mixing operation. So then the proof of negative conditional entropy is as follows. You can take the conditional entropy of the EPR state and you can add log 2 of the dimension of A. However, we know that the maximally uncertain state on system A tilde, if A tilde and A have the same dimensions, which we can suppose here, that this will simply be log 2 of the dimensions of A. So we can replace the second term with the entropy of the maximum uncertain state on A tilde. And we can then recombine these in the second line. Now, because we've identified in the previous slide that the channel is a conditional mixing operation, the entropy of this product state of the EPR state tensored with the maximum uncertain state on A tilde cannot decrease under this conditional mixing operation. And so we obtain the inequality here. However, since our channel involves measuring the involves a measurement that corresponds to the EPR state or its complement, we're always going to obtain the first outcome. And so the pure state, state 1, will always be prepared here, and the entropy of a pure state will be 0. So then upon rearranging, we find that the conditional entropy is not only negative, but also we can identify its value as negative log 2 of the dimension of A. And so in summary, we've formulated a simple axiomatic approach to quantum conditional entropy based on 2 sensible and simple axioms. We've used these axioms in a simple proof to conclude that quantum conditional entropy is negative for certain entangled states, and we've specifically shown that for the case of the EPR state. One of our open questions is we've identified a lower bound on the conditional entropy and have shown that that's achieved for the EPR state. We would like to also show that the conditional max entropy is an upper bound. So that's an area for potential future work as well. That concludes the presentation that I prepared. Happy to answer any questions.
Thanks a lot for the very nice presentation. Do we have any questions from the audience? We have a lot of time, so please don't shout. Well, maybe I can start with one. Is it known how to characterize these conditional mixing channels? Do they admit some nice characterization, or are there nice criteria or that one can use to show that a channel satisfies this?
I'm so sorry, my audio is having a bit of trouble. Would you mind repeating?
Oh, maybe. Yeah, if these conditional mixing channels admit some nice characterization. Like, because for the mixing channels, it was just being unital, right? Is there a similar simple criteria to show that one of those, that a channel is conditional mixing? Was that question clear now?
Yes, thank you. That's a good question. I believe that Dr. Gore, one of the co-authors, actually found this week that the for the classical case, that the conditional mixing channels relate to the set of conditional doubly stochastic maps. So maps where you're performing essentially a sum over J of individual mixing channels of DJ tensor Fj on the different systems.
I see. And but quantumly nothing is known, or
I think we recently showed that the maps, which are conditional mixing, correspond to that set of conditional doubly stochastic maps.
Okay. Okay, I see that Nilanjana raised her hand, so please, Nilanjana, go ahead.
Yes,
Nilanjana. I think you're muted, or
Hi there.
no.
Yeah. Thanks, Sam, for this nice talk. If you know the Renyi entropy, right? So the classical Renyi entropy, and there are various ways of generalizing it to a conditional Renyi entropy. And we had looked into this question, and there is one form of Renyi entropy due to Arimoto, or the Arimoto Renyi entropy. And if one wants to look at these various conditional entropies and wonder which one is the correct one, so which leads us to a similar axiomatic way of looking at things. And then we found, according to us, what we found, what we thought was most natural was one of them to take, for example, hx given y to be less than equal to hx. Why? Because if you know, get rid of the uncertainty of the one random variable, which is the y, then you should be having less uncertainty. So hx given y less than equal to hx. And the other one was a lower bound that hx given by cannot be too less. It cannot be, so it should be greater than equal to hx minus the logarithm of the dimension of the y alphabet. You see, these are two very natural axioms. So how do these compare with so there is a reduction in uncertainty if you know one random variable, but the reduction cannot be more than the knowledge you gain about the other random variable. So how do these two, which I consider quite natural axioms, compare with your axioms? Let's just stick to the classical case.
Yes, I'd be very interested to read your paper. It sounds very closely related. And may I ask how you, it certainly makes sense that you'd want the conditional entropy hx given y to be less than h of x. May I ask how you specifically came up with the second axiom, kind of bounding the maximal reduction in conditional entropy that you could have?
Yeah. What do? We look at Shannon entropy. Yeah, Shannon entropy satisfies that, and it is also intuitively clear because the reduction in uncertainty cannot be. Why is your uncertainty being reduced? It's because you're gaining knowledge, right, or information. So the reduction in uncertainty cannot be more than the amount of information you gain, and the maximum amount of information you can gain is the logarithm of the alphabet size, right? But don't worry, I just wanted to throw this out there and we can discuss this later on.
And so then the did you find sort of similar, I guess when you're asking how it compares
with your basic axioms?
I guess, yeah. So the sorry, there's quite a few slides. The consequences that we find are here. Were you able to find, I guess, were your consequences identical or something?
No, no, it was not a question of consequences.
Oh, okay.
These two criterion, which we can almost look at as axioms,
Yes.
it isolates the Arimoto-Renyi as the right, quote unquote, right way of defining the conditional entropy arising from the Renyi entropy. Yeah, so those were the axioms which isolates the Arimoto-Renyi compared to many other possible definitions of conditional Renyi. So that, but let's take this offline and we can talk about this. Yeah.
Yeah.
Thanks, Nilanjana. Any other questions? Well, then let's thank Sam again, and let's take a break for the